Hello everyone. Today we're going to go ahead and spend a little bit more time on section 4.5, L'Hôpital's rule. So go ahead and find this one on the right in your notes again, and we'll actually go ahead and do this for a warm-up and just to recall what L'Hôpital's rule is. So I'm going to go ahead and erase the answer and we'll actually go through the steps. So what we're going to go ahead and do is remember to just try and take the limit like we did back in chapter 2. That is to say, look at the value we're approaching and try to evaluate that in the function. If we plug in 0, we get the square root of 1 plus 0 minus 1 divided by 0, which of course is 0 over 0. And as we discussed last time, is a type of indeterminate form. So L'Hôpital's rule says if you take the top and the bottom and look at them separately and take the derivative, it'll have the same limit as the original. So again, we're not taking the limit here. We're taking the derivative of the top, which is 1 over the square root of 1 plus x. And then, of course, the derivative of 1 is 0. And then the derivative of the denominator is 1. So again, we took the derivative of the top, which is right here, and the bottom, which is right here, separately. Now, of course, this could clean up a little bit, so I'm not going to take the limit yet. I'm going to just go ahead and just realize that this is just 1 over the square root of 1 plus x, which then if you evaluate at 0, is the square root of 1 plus 0 in the denominator, which indeed just works out to 1 over 1. But in my haste, I made a mistake. Let's see if you can spot the mistake. If you are thinking, hey, you didn't take that derivative correct, then you are correct. There was a mistake right here. Remember that when I take the derivative of the square root of x, it is going to be 1 over 2 square root of x. So that's just a little mistake right there. So that would make this 2, this 2, and our answer 1/2. Sorry about that. But there is, again, an application of the derivative using L'Hôpital's rule to find the limit. So now that we remembered how to use L'Hôpital's rule, let's go ahead and look at other indeterminate forms. So we've completed most of this yesterday, the infinity over infinity, but let's again go ahead and do one more, just remember the context of how to think about the indeterminate forms involving infinity. So again, let's go ahead and look at this one and actually work it out from the beginning. So this one, when you consider the limit as x goes to infinity, remember, this is really when we're thinking about asymptotes and things like that. So if you were just to look at ln of x, so let's go ahead and look at ln of x. Remember that its graph is in the form of this. So if you were considering as x goes on to infinity, it grows rather slow, but indeed it still does grow without bound. So ln of x, as x goes to the right, this indeed does grow without bound, goes to infinity. And again, if you were to go ahead and just consider another function, the 2 square root of x, the square root of x function looks like this. And again, it doesn't grow very fast, but it still does grow without bounds. So, and this is another scenario where we have infinity over infinity. So we can use L'Hôpital's rule. And we'll go ahead and do that by taking the derivative of the top and the bottom separately. The derivative of ln of x is 1 over x. Then the derivative of 2 square root of x is 2 times 1 over 2 square root of x. Being a little bit more careful this time with my derivative. Of course, the 2's will cancel, and we actually could really simplify this one quite a bit. So again, I'm going to simplify before I try to consider the function. So this right here, this next step, I'm not using L'Hôpital's rule. I'm just going to go ahead and cancel my 2's. And multiply by the reciprocal. So this is 1 over x times the square root of x over 1. So again, I've just taken this and multiplied, instead of dividing, I multiplied it by the reciprocal. And it may even be useful to think about this as x to the 1/2, because if you go ahead and look at this as in terms of how can I simplify the exponents, realize that they both have the same base. The base of these exponents are both x, so you would just subtract the exponents. 1/2 minus 1 gives you negative 1/2, or you could think about this in just terms of we're going to have x to the 1/2 still in the bottom. That we have 1/2 cancels at the top, and then the half still remains in the bottom. But notice again, this is actually something we can't use L'Hopital's rule with. But if you think about the denominator is growing without bounds. So the denominator is going to infinity. The numerator is fixed. So it's the case of like 1/2, 1/2, 1/4, 1/100, 1/1000. Realize that this is just going to 0 if you consider it as a limit. In other words, the limit is simply 0. So let's go ahead and now look at a few scenarios where you have to do a little bit more setup before you use L'Hopital's rule. So again, notice L'Hopital's rule has been requiring us to use essentially some sort of rational function. L'Hopital's rule requires a function in the numerator and a function in the denominator. It doesn't matter when we check for indeterminate form, but we'll go ahead and do that first, but we're still going to need to do something in order to go ahead and get it a rational function. So you can see right here, we're going to be looking at another indeterminate form where you can have infinity times 0. So again, the temptation is to say, oh, this is 0 because you're multiplying by 0. But it all comes really back down to the fact that infinity is not a number. It's a concept that something's growing without bounds. It's a description of the behavior of the function. So again, to just kind of check that it's indeterminate, we can go ahead and look at these two pieces. Well, if you plug in pi from, again, remember this is not negative pi. We're looking at pi from the left-hand side. So I'm gonna actually adjust this problem a little bit, because realize that if I plugged in pi, that this would not go to 0. So let's go ahead and do a quick little adjustment and make this, let's go ahead and consider this as negative pi from the left-hand side. So let's go ahead and do that just so it's a little bit more illustrative. All right, so now if we plug in negative pi, this is going to be 0. And just remember the cotangent function. The cotangent function has asymptotes at multiples of pi. So the cotangent function is going to look something like this. So when we approach pi from the left-hand side, this is going to negative infinity. So this right here is basically 0 times negative infinity, which is indeterminate. Determinate spelling. So now we know we can use L'Hopital's rule because we verified it's an indeterminate form, but we're still not in a scenario where we can use it. So in order to go ahead and use L'Hopital's rule, I'm going to consider the limit as x approaches negative pi from the left-hand side, but I'm going to use the reciprocal function associated with cotangent. That is to say, I'm going to use x plus pi over tangent of x. So again, this is equivalent to our original function because we just switched the trigonometric function we were dealing with. So again, L'Hopital's rule requires us to have a rational function that is a numerator and a denominator, and sometimes you'll just have to do a step like that. Now, I already checked that this was indeterminate. Again, you could have even checked it here. You would have had 0 over, and tangent would have been tangent of pi. That would be 0. So you would have, I think, 0 over 0 here. Cosine, yeah. So again, doesn't matter where you check it. This would have been 0 over 0 if you want to consider that. Okay, so let's use L'Hopital's rule. So take the derivative of the numerator and the denominator separately, and it'll have the same limit as our original function. So the derivative of x is 1. The derivative of pi is 0. So there's the derivative of the numerator. The derivative of the denominator, well, remember the derivative of tangent is, if you take 2 seconds, you'll get it, a secant squared. And again, if you notice here, the 0 we don't necessarily need to write. We could just write this as 1 over secant squared. This is not an indeterminate form. This would be like 1 over, well, you could, it's one of those things, like whenever I'm thinking secant, I'm like, okay, secant's related to cosine. So I find it easier to simplify just this in terms of the reciprocal functions. Excuse me, secant is not equal to cosine, it's equal to 1 over cosine. So I'm going to rewrite this as cosine squared of x, because this is 1 over cosine. So when you have 1 over cosine squared of x, that's going to end up going to the numerator, which is where I got this. And now if you evaluate cosine at negative pi, remember that the squaring occurs afterwards with this notation. So I'm going to evaluate cosine at negative pi. Remembering our unit circle, this is where we're at with negative pi. So that is going to be, cosine is going to be negative 1. So we have negative 1 squared, which indeed is just 1. All right, so again, if you are feeling pretty confident with what is happening, we had those who were in the Zoom meeting while I recorded it, were trying this one. So here's the explanation. And again, you may want to pause the video and see if you are comfortable with it. I just erased a little hint, so you can always back up and see that hint again if you need it. But here's the explanation. So again, it does not matter when you check if it's indeterminate form. You can go ahead and check it right now. And if you look at this right now, when you plug in 0, this is going to be 0. And then just remember ln, as x approaches 0 from the left-hand side, you do have, again, an asymptote there at x equals 0. So you do have a indeterminate form. So again, the trick now is to go ahead and turn this into something that you can actually use Hôpital's rule with. Now that we know it is indeed an indeterminate form, let's go ahead and transform this into a rational function or something that has a numerator and denominator. And we're going to simply do that by undoing the multiplication by a reciprocal. So ln of x will stay in the numerator, but the denominator I'm going to rewrite as 1 over the square root of x. And if you think about multiplication by the reciprocal, the x would end up in the numerator, or the square root of x ends up in the numerator, which is how we got our original problem. Now, again, you may choose, just to get this ready to take a derivative, you may choose to write this as ln of x over x to the negative 1/2. Remember that this x does not cancel with this one because the ln of x is, the x is trapped by the ln, is the input to an ln function. And if you even look at this again, this is still going to be negative infinity over 0. So we still have this indeterminate form. Now let's apply L'Hôpital's rule. So what we'll do is take the derivative of the numerator, which is going to give us 1 over x, divide that by, well, this one's again, just remember the power rule. I'm going to do this off to the side. Is going to give you negative 1/2 in front, then x to the negative 3/2 when you reduce the power. So what this comes out to be is negative 1/2 x to the negative 3/2. And again, there's a lot of fractions here, so it's really just a matter of being very careful with what you're looking at. What you could go ahead and do is, I'm going to actually, instead of writing it as x to the negative 3/2, I'm going to set this up so it's definitely, you could definitely see the fractions. So I'm going to put the 3 halves, x to the 3 halves in the denominator of the denominator. And of course, when I put it in the denominator of the denominator, it's going to be a positive 3 halves. So let's try that. That looks a little bit sloppy. So 3 halves. Now let me use a smaller pen. So 3 halves. There we go. Okay, now we can think about multiplying this by the reciprocal to just go ahead and clean up the fractions. So it is the whole thing's to be negative because that one negative in the denominator. Then we have 1 over x. This was our numerator. Multiplying this by 2x to the 3 halves over 1 because of multiplication by the reciprocal. Again, this is just a matter of dealing with these fractions. The compound fractions, a little bit tricky, but that tends to introduce itself when you're considering the derivative of a denominator because a lot of derivatives have powers which may introduce fractions. Now, if we take one more step before plugging in, again, you can't plug in here because you have 0 over 0, but you could use L'Hopital's rule, but notice what happens when you clean up. You have 1x in the denominator and 3 halves of an x to the 3 halves in the numerator. So just do 3 halves minus 1 to get 1/2. So that means you have x to the 1/2 in the numerator. So what this is right here is -2 from right here and here, then x to the 1/2, which this you could plug in 0 for and just get 0. So there is the limit for that associated problem. But again, the trick here is figuring out how to turn this into something you can use with L'Hopital's rule. So we're going to look at a few other scenarios. So let me just pause for questions. And again, if you are watching this video later, just go ahead and pause and make sure you understand everything that's happening. So on this next one, we're going to look at another type of indeterminate form, which infinity minus infinity, which again is not 0 because infinity is not a number. It's a way to describe the behavior of a function, typically with asymptotes. So again, if you think about the limit as x approaches 0, just remember that 1 over sine of x is cosecant of x. And cosecant's graph, just remember where asymptotes are. So if we look at sine, sine's graph looks like this. So right here, so that means cosecant's graph, it basically uses sine's graph as a jumping off point, is the way I think about it. And we do indeed have an asymptote right there at x equals 0 for cosecant. So that means that indeed this is going to be, it's going to be infinity, whether you consider the left or right hand side. The behavior is at infinity, either plus or minus there. Then 1 over x, again, 1 over x just is going to look like 2 curves. Just look at those curves right there. So fancy. Anyway, that again has an asymptote there at x equals 0. So again, this is of the indeterminate form, infinity minus infinity. So that means I could apply L'Hopital's rule. Notice again is we don't have one rational function. This is not f of x over g of x. And you can't just take the derivative of this because this one right here is, again, this is not indeterminate. This one is not indeterminate itself. But when you think about them together, it's an indeterminate form. So what I'm going to simply do is get a common denominator and combine them. That's another way to go ahead and get them into a single fraction that you can use L'Hopital's rule with. So what I'm going to do is multiply the first one by x over x. So this is just going to give you x in the numerator. X times 1 is x. And the second one, I'm going to have to multiply by sine of x and sine of x. So this will give you minus sine of x in the numerator. And then the denominator is just going to be x sine of x. And again, if you did that step first, you may notice that this is 0 over 0. So this is, again, an indeterminate form, stays an indeterminate form, unless if there's some sort of cancellation like there was in the last problem. So the last problem we had like the 3/2 over x, which canceled, and that's no longer indeterminate. So again, we've already verified that's an indeterminate of 4. It's still 0 over 0 here, so you could still apply L'Hopital's rule. This one a little bit tricky, but I just wanted to illustrate the way that you combine this indeterminate form into something you could use L'Hopital's rule with. Again, this a lot of derivatives really is where you master your algebra. So let me help you through this one. So taking the derivative of the numerator, no problem at all. That is just going to be 1 minus cosine of x. Derivative of x is 1, derivative of sine is cosine. Denominator, we will use the product rule here, because this is the product of x and sine of x. So it's first times the derivative of the second, plus the second times the derivative of the first. Product rule. Okay, now if you plug in 0 here, you get 1 minus cosine of 0 over 0 times 1 plus 0 times 1, which is 0 over 0 when everything is said and done. So again, I kind of went through that a little bit quickly, but cosine of 0 is 1. So that is 1 minus 1 to give you 0. And same principle happening down here. All right, so that means we're going to have to use L'Hopital's rule again. Unfortunately, we'll have to use the product rule and the addition rule here. So I'm going to just erase the 1 because that's just cleans it up a little bit. Hopefully at this point, you're definitely okay with the derivative of x being 1. So L'Hopital's rule again, I'm taking the derivative here, is going to be a positive sign in the numerator, because the derivative of cosine is minus sine. The two minus signs are positive. Product rule here again in the denominator. So with this x cosine of x, I'm going to need to use the product rule. First times the derivative of the second plus the second times the derivative of the first, which is 1. Then the derivative of sine is going to be cosine of x. So again, this is where you had to be really comfortable with your derivatives, but you could go ahead and rearrange things if you want. But if you plug in 0, what we're going to find here is that sine of 0 is going to be equal to 0. But this denominator is going to be 0 times 0 plus 1 plus 1. And again, I would encourage you just to think through this. Cosine of 0 is 1. So that's where these come from. And of course, this disappears because of the 0. So you have 0 over 2, which is 0. So again, that's just an illustration of an example where you could go ahead and combine fractions in order to create a function you could apply L'Hopital's rule with. I think I just like saying L'Hopital. Just kind of rolls off the tongue. Try it sometime. Anyway, I'm going to pause for questions. So let's go ahead and look at one more type of problem. And this one's not in the notes. I added it to it afterwards. So I'm going to go ahead and give you a moment to go ahead and copy it down. And but it's going to be indeterminate of forms like this, where you have like 1 to infinity, 0 to the 0, or infinity to the 0. And we'll look at a few cases where these show up. These show up when we're looking at transcendental functions. So these were introduced back with implicit differentiation. And logarithmic differentiation is one way we look to take the derivative, but we're going to go ahead and use just a little kind of algebraic maneuver to go ahead and get this into a form that we can use L'Hopital's rule. So go ahead and take a moment and write those down. And we'll go ahead and try the first one, then I'll just go ahead and give the solution to the second one, since we are running low on time for at least those that are with us. Again, if you're watching this video recording later, it's a lot shorter because I'm pausing regularly to answer questions. Okay, so let's look at this first one. This first one is of the form 1 to the infinity. So this is that first indeterminate form that we have listed above. So this is 1 to the infinity. Again, why? Because if you plug in 0 here, that's where the 1 comes from. And then just remember that 1 over x has an asymptote at 0. So we do indeed have the infinity as we approach 0 from the right-hand side. So the thing here is we don't have a fraction that I could apply L'Hôpital's rule with. So what I'm going to do is I'm going to essentially go ahead and add some extra terms here. And I'm going to go ahead and write it, then we'll pick it apart. Y is equivalent. So what I'm going to do is I'm going to look at the limit of an exponential function, where the exponential function I'm going to cancel out with a natural logarithmic function. And then inside that natural logarithmic function, I'll have my original problem. So let me color code this. 1 plus x to the 1 over x. So let's go ahead and just look. Why is this equivalent? Because remember, e and ln are inverses. So when these cancel, whatever was in the ln is what's going to be here. So that's our original function. So this is just an algebraic trick, algebraic maneuver, and this shows up quite a bit in calculus too. As you go ahead and learn how to deal with infinite series, you need a way to simplify those, get things out of the exponent. So what this is going to allow us to do is to use the power rule to go ahead and bring the 1 over x in front of the ln. So what we're going to do is focus on just the, let's see. Actually, I'm going to explain this two ways. I'm going to go ahead and simplify this a little bit first. I just want to go ahead and simplify the problem like so. So if you remember, the can be brought inside a composition. So what I'm going to do is this e, I'm going to bring out, and I'm going to bring the limit inside the composition inside the e to the x. So I'm going to be looking at the limit as x approaches 0 from the right of ln of 1 plus x to the 1 over x. So again, what I am now going to do is find the limit of this right here. Limits could be brought inside compositions. So again, this is a composition function where e is your outer and this is your inner. So I just brought the limit inside. So let me now focus on that highlighted pink. So this is like a new subproblem. So I'm going to do this in a completely different color, just so you could see how would I find the limit of as x approaches 0 from the right of ln of 1 plus x to the 1 over x. It looks pretty nasty, but remember what the power rule allows us to do. The power rule allows us to take this exponent and move it in front of the ln. In other words, we're looking at the limit as x approaches 0 from the right of 1 over x times ln of 1 plus x. We all of a sudden just got our natural logarithm by itself at the top, and we have a rational function we can now apply L'Hôpital's rule with. So, by the way, you could even see right here, if I rewrote this as x approaches 0 from the right, of ln of 1 plus x over x. If you consider this is 0 over 0 again, so it's still indeterminate through all of this. It's indeterminate. But This you could apply L'Hôpital's rule with, and it is just going to be the limit as x approaches 0 from the right. 1 over 1 plus x is the derivative of my numerator. The derivative of my denominator is indeed 1. So now take the limit. You get 1 over 1 over 1, which is 1. And you're like, whew, am I done yet? And you're like, oh wait, I'm not done yet. Because remember, this is a subproblem. This is the answer to that. Where is that? That's on the E. So end subproblem, return to original problem. The actual answer is here, and I'll go ahead and write it. The answer to our original, the limit as x approaches 0 from the right of 1 plus x to the 1 over x is equal to e to the 1, where e came from here and the 1 was the solution to our little subproblem. Again, that one's a little bit tough, but it's an illustration of how to go ahead and work with limits of transcendental functions, something that we couldn't have done earlier in the semester. But that really completes the discussion of Calc 1 in the context of limits. You look at something known as series in Calc 2, where limits are used to help you figure out the convergence of series. So the answer to this second one over here is going to, when all is said and done, is going to be -1. And I'll also post a complete set of notes that has the solution worked out. I would encourage you to go ahead and just try and think through that one, see if you're able to get it. Remember to continue to work diligently. If you have questions, I'm always available. But we are nearing the end of the semester. So just know that I'm praying for you as we are really just powering through to the end. Let me know if you have questions, and have a great day, everyone.